All right. Do people know? Do people have the link? Okay. It should be started.
Okay. How about now?
Where could that be?
Hello.
Seems to be all right.
Okay.
People have the link. Okay.
Let's see. Can you see the slides on the Vikash?
Yes, I can see the slides and Vikash. Last time I couldn't hear me very well. Vikash, can you say something?
Yeah. Can you hear me now?
Yeah, now. Perfect. Yes, I can see the slides and Vikash.
Okay. You're still waiting for Emma.
And it might be more exciting. Okay. And I've got your slides here so I can follow along with the slides that you sent me.
Okay.
So that's good.
Oh, 7 people are watching.
Emma knows, right?
Emma knows. I called him and he's like, why do you want me there early?
Where is he? Is he already on the bridge?
Yeah, that's right. That was,
Yeah, he's always on the bridge.
Relatively speaking, when he gets out of bed, he's already really close.
In Cece's words, which is Emma's wife, she says like Emma has no notion of time.
But you do know that I have a hard deadline at 1:20.
sit in this. Right.
Yes.
Exactly.
Maybe we should.
The GSM reports will be Emma's reports.
They should be. So, because does Emo bring the report? The GSM.
He's supposed to bring it.
I know.
I can run down and bring the report before him. It should be mailbox, I think. Yeah. Okay.
Already possible.
How you guys doing?
Good.
Are you collaborating with
You literally just put it down in front of me.
Call Emma.
Did you?
Yeah,
You
Emma.
call
Emma.
Yeah, yeah. So you can do something together. Yeah, I'll do more on the conception side.
I know from JP.
Okay.
You joined after, I guess.
Yeah, I remember that year when
9 viewers now.
I also thought it was very
Oh, voicemail? Yeah, I think we are still interested.
He already knows this.
He knows this. I talked to him like 40 minutes ago.
you think this
He's stuck in traffic, of course.
I think
I was like, Emma, really early. And he's like, why do
that's
you
what
want
the
it there?
So, I don't know.
So he talked to him after he started at Stanford.
I think when he got the position at Stanford. Is a way that I can, come there.
So he's been there now for a year.
We'll see.
I talked to him at a conference recently this year.
Oh,
And he sounded
Oh, there it is.
no, he sounded very interested.
Yeah.
Like he would have liked it.
All right.
And he would have liked it. So I think he
Thank you.
It's on silent, right?
Yes.
Yeah.
You put it on silent? I'm going to turn all the sounds off.
All right, let's start. I think everyone who should be here and is actually required to be here is here. So thank you everyone for coming. I know it's raining pretty bad outside and it's hard to get here, but thanks for coming. This is my final exam. And in case you haven't guessed, we'll be talking a lot about hands. And hands are interesting to one and everyone. They are the most complex form of biomechanical structure that exhibits such complicated properties. And they have been widely studied across different fields. in biomechanics, neuroscience, graphics, animation, rehabilitation, and even robotics. But despite all this attention, our understanding of hand is very superficial and far from being the purpose for it. If we look at how the nature solves this problem, it comes up with a very complicated structure of tendons and soft tissues and bones to make this happen. And to control this complicated structure, an incredible amount of brain power is required. As if this brain power is not enough, we have evidence for low-dimensional embeddings and synergy spaces to make this happen. So if nature's solution is so complex, and at the same time is it at the intersection of both hardware and computation, probably we should study at the same intersection. So the talk and my thesis title is Manipulators and Manipulation in High-Dimensional Spaces. And here is a quick overview. First, we are going to understand what a high-dimensional and flexible manipulator and capable manipulator is. Designing such a system comes up with a cost. And we are going to cater to that cost using this the second topic, which is hardware abstraction, which is going to make our manipulator even more functional. We are going to study the behaviors of this manipulator in the third section, and this third section is very tightly coupled with the first section, where we go back and forth and design behaviors for the manipulator and get informed by those behaviors and come back and change the design. And in the fourth part of the talk, we'll plug all of these things together to get manipulation hopefully on the hardware. Okay, so let's start with the first part. It's manipulator design. And if you look at the figure on the left side, that are the most functional manipulators that are now available. The overarching goal of this, of the overview of this is most of the manipulators are fairly simple and they are task specific. They do one job and they do it well. It's not that flexible manipulators don't exist, but we don't know how to control these manipulators properly. So here is how they lie. If we try to increase the flexibility of the manipulators, then the performance of those manipulators goes down. And if we try to reduce the flexibility, the performance goes up. And ideally, the human hand lies in the top right over here, and that's where we want to go. And that's the drive of this thesis, to push towards that upper diagonal. Here is the manipulator that I have designed. It's called Adroit. And we are going to see Adroit in different forms. These are some of the renderings that we will be seeing throughout the talk. A very quick overview of what Adroit is. It's a 28 degree of freedom system, with 24 degree of actuated degree of freedoms. It's a pneumatically actuated system which has very low friction and stiction properties. It's a highly observed system, come up with a lot of sensors, joint angle sensor, touch sensor, pressure sensor to sense the forces, and tendon sensors to tell us what all the tendons are doing. Let's look at the physical properties of the system. What is this system capable of? Okay, now we are looking at the speed capabilities. It lasts for 2.5 seconds, so very quick. What it is showing right now is each of these joints both contracting and flexing one at a time, trying to show up the dexterity of the hand, at the same time the speed of the system. It is a very fast system which is able to take your commands and process it really fast. So we are going to study the reflex behaviors of the system. So the hand is instructed to act when it sees a perturbation. So we are trying to measure the overall loop latency of how fast the system can respond to you. And as you can see, this is very fast. These numbers, the numbers if we check here, are pretty comparable to human and even slightly less than human numbers here. It is a very compliant system because we want our manipulators to be deployed in the real world, so we want to be safe and compliant. So a small gust of hair is able to displace the finger on the null controls. That just gives you an idea of how soft and stiction-free and friction-free the hardware is. Towards the end over here, we will see how it feels if a human is trying to interact with the system. So it is very passive and very gentle system. If you look at the numbers are very comparable. Yes.
So you get that same behavior even if you have settings such that you can do the very fast motions at the same time.
So you are, in that case, if you're actuating against the human, then you will not get this behavior. It's going to be harder, but it's still compliant. You can still place your hand and not get hurt. And the numbers are very comparable to human numbers. Only the strength is not as great as human, where we can use the power tools, but this is only good till day-to-day daily objects, but not good enough for power driven settings. So what we have achieved right now is, hello? So what we have achieved now is a very capable system, but comes with a price. And the price is the dimensionality of the system is very high, and the control is complicated because of the pneumatic system. And we are going to address these two challenges throughout the rest of the talk, and we're not going to ignore these challenges. So to address one of those two, we'll start with the control. And we are going to say that how do we cater to the complications from the control? And this section is the hardware abstraction section. But the first question we'll ask is why even go for this complicated control, which is the pneumatic control? Because it comes with a lot of positives. It is a compact system, it's lightweight, it can be bundled together, there are less number of moving parts, so it can last longer, and it has compliance at the mechanism level. And it has properties which is very comparable to biological muscles. So it is very desirable. But on the back side, what we get is it's a third order system. The air is compressible, so that means we have very low bandwidth of the system. And the dynamics is very sensitive because of the volume change, and it becomes harder and harder to control. So the idea in this section is to make a hardware abstraction layer that hides all of these negative effects. Let's understand this in detail using an example. The position servos are the most successful actuators till now. We have seen them everywhere, and they have been widely successful in automation, industry, and stuff. And what we have done in this particular abstraction is we hid all the details of the gears, backlash, friction, stiction, and motors, and enclosed it into a black box that takes shaft positions as inputs. So we have reduced this complicated system into a system that we understand well because we were used to planning in position space. But now what we have is planners that plans using mathematical models. So using the same analogy, what we can say is, if synthesizing behaviors using mathematical model is what is intuitive for the planners that we use today, why not build such black boxes which is intuitive for these planners? And that is what we are going to do. Here is what traditionally happens. There is a task. We give a model to the planner, and the planner uses both the task and the model and comes up with the policy, and we use that policy on the hardware. Since this model is different than what we have in the hardware, this is not going to be exact, and we try to patch it using a residual modeling. And this gets complicated because this model is very noisy, and the planner's job gets harder and harder as you make this model harder and harder. So what we propose is we are still going to play this game, but instead of playing it here, we are going to play it here. We are going to still keep the physics model simple, and we are going to put an abstraction layer on top so the hardware becomes better behaved and closer approximation to the model we have. What does it look like for the pneumatic system? We're going to build a hardware abstraction such that the pneumatics now starts to behave like a force actuator. And we all know the planners today know how to deal with force actuation. The first question I'm going to ask is it even possible to come up with a force actuator, because we just said the dynamics is very sensitive, it's slow, and the bandwidth is very low. One successful example that we have seen is biological muscles, and the time scale is comparable to that of pneumatics, and the way we deal with those time scales is by anticipation. Before we run, we cleanse ourselves and then go for it. So we prepare before we act, and we are going to play the similar game over here. So very quickly, once we have a planner gives the policy at any given time t, we use that policy on the hardware itself. What we are going to do instead is now we are going to give the policy at time t plus a little bit of future. So now the planner here is well aware of what is coming in the future. And this hardware abstraction layer is nothing but a trajectory optimization. So there is going to be a trajectory optimization in there which solves for controls given the present as well as a little bit in the future. Let's quickly look at what a trajectory optimization is. It takes two things as an input, a dynamical model of the system, and some notion of a goal, which we encode in cost. And there's an optimizer which takes these two things as input, does a bit of dynamic programming. The particular one we use is iterative LQG, and it produces behaviors. So we are going to play the same game. The first thing what we need in this paradigm is the dynamical model of the system. And we have been talking a lot that the model of the pneumatics is very complicated. So very quickly, I'm going to sum up a lot of work in just one slide and move on from there. This is the model that we have developed. It's a physics-informed model. So it's a highly physics-based model. It relies on pressure, the controls, the volume, the rate of change of volume, and the two pressures, the compressor and the atmosphere. It's a physics-based model, and it's very sensitive because at small volume, the dynamics changes rapidly because the volume comes in the denominator. And for large volume, it's pretty slow. So there is another model that we have created, which is much more, it's the data-driven model. But the properties of this model is a linear ODE, and we can analytically integrate this forward. So that allows us to take longer steps. So both of them have their own benefits. One is more precise than the other. So here is the tracking error that we see of both the models. The blue is the physics one, and the red is the data-driven parametric model, and they are quite comparable. And this is 5% of the total pressure swing. So we have less than 5%. But this less than 5% also means 2.5 newtons of force. So 5% is also a significant amount of force here because pneumatics just gives us this a lot. And on the right, we see, whereas physics-based model is very detailed, has complicated curvatures in the dynamics, the parametric model is very flat and gives significant approximation. So now we have the model, which is the robot of the system. We have some goal which just says track current as well as pay attention to the future, and we are going to solve this trajectory optimization problem inside the hardware abstraction layer. What we achieve is something like this. So the goal here is to control this toy example. The red is what the desired trajectories are, and the black is what actually happens. So at any time t, we see that the error is building up, and the simple PIDF, which is a fancier version of PID, which does better than PID, sees that error and tries to improve that error. Whereas what we see in our approach is even before when that error is about to happen, the system is actually prepared to correct that error. And it does better in tracking. And we see that also in the pressure that both the cylinders, both up and down, are preparing for that thing to happen, which is clenching of the muscle. And as soon as the movement has been achieved, all the muscles relax in time. If some of you were in the colloquium before, this sounds very similar to what everyone has been talking about as a goal-directed dynamics, where you have the dynamics which is complicated to control, but you wrap it inside an optimization and build a layer around it, and you have a now new dynamical system, which is somewhat easier to control.
You're also optimizing the look-ahead K, or is that?
Sorry?
The look-ahead.
The K is given. We pick it based on performance. It's not being optimized in all. We use 250 milliseconds. So let's look at the performance we achieve for force actuation. This is a little hard to see, so I'm going to zoom it in a little bit. So the dotted lines is what the desired are. The actual pressure is in solid line and control is in red. We will focus on these two graphs for now. So we see very good tracking results. And the controls that we come up with is not very trivial, even for sine waves. It doesn't reflect sine. It's some notion of sine that is a little bit different. What we are going to see on the right side is a very interesting graph. Let me explain. So we have promised a future to you, but we are not sure if that future is going to happen. But a trajectory optimizer or your planner can change the future when it arrives. So here we play the game that we tell you that there is a future, but we are going to change the future completely, and you have to deal with that. So the tracking performance take a little bit of hit, but we don't go unstable. We still do pretty good. What we are going to see on down below is robustness, where we use a model from one cylinder to another cylinder, and it still works. The error is a little bit more. So that should be it. Like we have a pneumatic actuator that behaves like a force actuator. That should be the solution. But what we have solved is a problem for this, and what we need is a solution for this. It's a 50 times scale. And it's pretty huge scale up given all of the individual trajectory optimization on itself is a computationally expensive job. And it does it using parallel multiple threads. So in order to solve this problem, what we are going to do on the left is the state of the system, is the pressure. On the right is all the valve commands. And we are going to actually chop it up into small chunks. And for each of these small chunks, we are going to use one pool of hardware abstraction. And we are going to create multiple of those. So all of a sudden, this is a very complicated, computationally expensive multiple, which is parallelized within the pool and across the pool. So it definitely overwhelms the machine. Nevertheless, it does its work. We are not using GPUs. The results are on 24 cores normal desktop, but it's definitely a powerful desktop. Let's look at the numbers. How do we pick how many pools to use and how to chop it up? So on the left, we'll see we pick 2 actuators and 20 different pools. That means each pool has 2 actuators, has to deal with 2 actuators. On the right, we say all the actuators are plugged in one pool. So this is just the scale, and we say somewhere in the middle there is a sweet spot, and that is what we are going to pick is 8 actuators and 5 pools. So each pool caters to 5 actuators. And as we increase the number of actuators, as expected, the time to solve for the trajectory optimization goes up because the dimensionality of individual actuators is going up. How do we do for this system when everything is working together properly? Okay, I'm going to zoom in a little bit. Here is the desired. The solid line is desired. The green is what we are doing, and the blue is what the PID does. So we already see that the PID is lagging pretty bad. If we increase the frequency of the system, PID goes anti-phase. If we further increase the system, the PID has already entered the resonance because we were anti-phase, we are lagging, and this is the resonant frequency. This is not even a controlled system now. And this is the best performance of PID. What actually happens for most of the actuators is like this. There is a transient load riding on top of the PID that makes the whole system uncontrollable. And even for high frequencies like this, we see pretty good performance for all the actuators for our system. So that will, yes.
Okay. Do you, every time step when you get this future window, do you optimize from scratch, or can you somehow reuse your?
We reuse the previous optimization that you see, and then that is what brings us into real time.
Sorry, so you're solving M8 MPC.
Yes, in parallel, and each one of them has 5 actuators to do it.
And they're coupled, or
each of these actuators are not coupled because we want the system to have the maximum flexibility. So higher level planner, if they want to give a coupled actuation, each of the actuators still does its own job. So this is not coupled. Each one of them acts independently. That's why how we can distribute, how we can chop up the whole stuff.
Now
Yes.
that you're talking about this, is it somehow related to the structure of the hand?
No, it is
Related,
not.
or?
We can definitely do that, saying that if all the fingers work properly, perhaps we can club it together. But since we are solving the optimization problem independently, there is no interrelationship between them. They cannot. So we have to build that structure if we want to exploit it.
So this notion of a pool is just some kind of side effect of the way the multi-threading and the specific processor works.
Yes, yes. If you put everything together, like we said, 40 actuators in just one pool, it is not even real time. It doesn't even work. So this is very much informed from the hardware of the system. How many threads can be swamped? How fast we can run the execution of each one of these threads. So that concludes the hardware abstraction. So what we have done is build a capable manipulator and cater to the control deficiencies or control complication by building a hardware abstraction layer on top of it. The next section is going to be our behavior synthesis. And we are going to inform this section based on the priorities of the hardware. So previously, a lot of people have done complicated hand manipulation. But what happened here was we did search for some of these approaches on the top. We did search for the whole space and came up with good strategies, but they were flexible a little bit on the physics. But if we want to play it on the real hardware, we cannot do that. On the right is a purely geometric approach, which is a very successful approach called GraspIt, where it uses purely geometric approach. But for complication, when we are doing something like this, any plan is not going to succeed as it is, and we are going to fail as we start executing the plan. On the bottom below is some of the hardware results, and most of these results have been driven by human carefully reasoning about what the behavior should look like. So what is missing for all of these things is a notion of autonomy, because as we are going to do complicated maneuvers, every time our plan is going to fail, we'll have to readjust and come up with a better plan of the system. And that is going to be missing, and that is what we are going to cater to now. So before we go there, I'm going to put 2 definitions. One is movement. Movement just says change in any degree of freedom of a robot is a movement. It characterizes any sets of actions the robot can take, whereas a behavior is a coordinated set of movement that produces an outcome. And it characterizes the set of outcomes that it can produce. So traditionally, people have been reasoning about movements. They design these movements based on scripting, inverse kinematics, but what we are going to do is plan about behaviors, and we are going to deploy the same trajectory optimization we talked about a little bit ago, and using the tools of optimal control and this principle of encoding the goal in a cost function, we are going to solve this problem. And we are going to deploy trajectory optimization in a long predictive control fashion. What that means is at any given time t, we are going to solve a trajectory optimization problem. We are going to initially execute a small part of that plan, and we are going to re-optimize the whole plan before it even finishes. So at any given point, there is a plan. We are re-optimizing it all the time. And only initial part of the plan is ever being executed. Why does this is a good strategy? Because the model that we are planning with is not the model that we are executing in the real world. So the optimum, even if we find it, we can never actually fully achieve on the real world. So there is no point trying to find this optimum. We are just going to make as fast update as possible. The another important thing is we can use partial plans in the system. Instead of solving the whole trajectory optimization from start to goal, we can only solve for a finite horizon and encode some kind of final cost to encode the knowledge of the rest of the trajectory. So what this allows us to make quick updates because now we are solving for shorter horizon. And the fast replanning, what it allows us is to improvise on what the past has been. It adapts to the current while being aware of what the future is going to happen. So we have applied this problem, this framework to a variety of locomotion problems. But what happens when we apply this problem to manipulation? Behaviors, something like this emerges. So we can see like it's definitely trying to do the right thing, but it never succeeds. It fails drastically in understanding the notion of stability. So the problem, which kind of look like they are alike, is not completely alike. And let's understand what is different in both the systems. In one case, the stability of the is of the notion of the body. The body has to be stable. In the other case, the object has to be stable. The interactions are widely different in both the cases because in locomotion, the interaction for one is very principled. You are on flat ground, whereas in manipulation, the interactions are very complicated. It changes. The contact nature is also periodic and principled in locomotion, but it changes radically in manipulation. And the system itself is fairly complicated because we have tendons and small sensing elements, which is not great itself. So it is a very different system, which initially looked like the same system. Formally, this problem looks like a 68-dimensional state space, including hand and the object. There is 48 control dimensions, and there is a lot of constraints in the system coming from various limits. So the problem here is we have an object, and we want to put this object in a stable configuration, which can be anywhere, which is user specified. And the hand has to come up with strategy in order to make that happen. So let's look at the results before we move ahead. Okay, so here is the object on the ground. The stable notion was on the top. So what we see here is the hand was losing the object, and we went for replanning right there to throw the object back up in the air and come to the better strategy that actually works better. In the second case, it actually does a back fumble where it hits the back of the hand and re-strategizes again. So what we see right now is the hand is failing constantly, but it knows how to improve and recover from that failure. And that is what is important, that enables all these variety of different movements. In the next sequence, what we will see is the middle of the trial, we are going to change the notion of where the stable position is and put it back on the ground. So it ends up discovering this like pick up and place behaviors.
How much friction do you assume there?
There is normal friction. Okay, so here are where the various challenges in the problem. The optimization landscape is just nasty. It's high dimensional, it's nonlinear, a lot of discontinuities coming from various constraints, and these constraints and nonlinearities are evolving as the object is moving around in the hand. And there are lots of local minimas because of the dimensionality and not known to. And most of these challenges are coming from the fact that we are dealing with a lot of contacts, and contacts pose discontinuities in the system. We have roughly 22 contacts active anytime we have object in the hand, and we have seen maximum of 200 contacts in the system as well. Contacts are fairly expensive to compute and deal with, so we have come up with following simplifications or careful careful understanding of the contacts. And what we do is all the fingers only apply normal force, so you can get only pressure. All the fingers and the object can apply normal, and you can have friction. Whereas the fingertips, where most of the action actually happens, they have normal friction as well as torsional friction, where you can actually put friction on this as well as that. And the geometric shapes are used to compute the controls because these are well behaved and a little bit easier to control compute the contact forces. To deal with frequent discontinuities, most of these contacts are made such that the gradient is available when the contact happens and vanish. Similar is the case for while dealing with the constraint. Constraints are imposed such that the gradients are available when they actually move over. But now the system is such a high dimensional, and it worked for a locomotion because this high dimensional system had reduced abstractions like ZMP and inverted pendulum, which we used and leveraged to solve and come up with a solution. But such abstractions do not exist for hand as of now. So we are forced to deal with high dimensionality of the system with all the details of the physical hardware, including pendants, constraints, collisions, etc. And this is done using the Majoko, which Kamal thankfully has developed over here. And the progress of Majoko and this project were going hand in hand. So I was fortunate to do it. Putting everything together, it still doesn't quite work. There is this magic sauce. Yes.
So you say it wasn't available. So it sounds like you're arguing that because of that you needed to use a full fixed model. Could you have come up with a reduced model abstraction for that?
If we knew, then that would have been the first line of approach. But that reduced model just does not exist. We just have no idea how to come up with a reduced model. But yes, if that existed, that would be the first line of approach to go.
No, but I was wondering, could you put it into existence?
Yes, in principle, if I was smart enough, I could have done that.
Okay, so it's extreme.
People have tried to, it's not clear that such a thing exists.
Yes. It's either doesn't exist or incredibly hard to do. So there's this magic sauce, which is dimensionality augmentation. Everyone here in the room, I assume, has heard of dimensionality reduction. Reduction is when we take this full-blown state space, reduce it to submanifold, do the planning in the submanifold, and project the solution back into the high-dimensional space. But what it does, it kills the dexterity of the hand. But that is what we are trying to achieve. So what we are going to do instead is going to say, add one of the synergistic actuation dimensions into the existing high-dimensional space. So we are going to increase the control dimension by 1. So this is increasing the dimensionality, and this is what the control dimension does. It just closes and opens the hand. It is very simple, the first PCA axis. We didn't even bother to get the real PCA axis, we just made it open and close. And what it does, let's try to understand using an example. If we have dropped something, a ring, in the bottom of the valley, there are 2 approaches to take the ring back. One, I can start walking from here and eventually find myself in the bottom and find that ring. Or you take a cable car if it existed. Go quickly to the down as much as you can and get down and then look around where the thing is. This is exactly what is happening. Because what we have done is this one extra dimension that we have added is very cheap to choose. So whenever this extra dimension is available, the optimizer actually chooses that dimension and makes rapid progress in that dimension and then recovers and deploys the rest of the dimension only when the first dimension is not available. So whereas dimensionality reduction was killing the dexterity of the system, this approach is augmenting and preserving the dexterity of the system. And the way it deals with this complicated optimization landscape is by facilitating navigation in the landscape. I would like to point out that every behavior was encoded as a cost function, and no movement-specific cost function is provided. We just set abstract cost function that go here, this is the desired goal, etc. And for this particular case, the cost function was distance to the goal configuration, some regularization, and there is this third cost, which is a very faint cost saying distance between hand and object, saying the hand is far away and the object is not in your planning horizon. There is still some merit to actually go towards the object. And as soon as the object is in the planning horizon, this is very faint cost that doesn't play any effect after that. Few other behaviors have been trained. Typing is one of them. It types and goes for the dictation. So you can provide dictation in real time and it types and goes. In the interest of time, I'll probably skip that thing and maybe play it later if we have more time. Yes. You want to see it? Yeah.
Did you get this to work on the real world?
The performance was not great. We'll get to that. But yes, it did press a couple of keys. So the key is pressed when it's black, and the keys are spring-loaded. So it's harder and harder to press it more and more. And as you see, as we provide the dictation, the keys are getting highlighted, and you press, and the hand goes and press those keys. And it is not afraid of actually going and touching other keys, which is how we type as well, as far as left. We are also going to play nasty, and we are going to play evil, and going to apply perturbations. And because of this replanning strategy that we have built up into the system, it goes for a replanning as soon as it deviates away from the plan. All right, and there's the just command. Okay, let's see. So what we have done right now is come up with a behavior synthesis framework, which has amazing generalization. It works across a variety of task variation, has this replanning properties. But the thing that I have not told you up to this point is it is assuming a perfect state. If given a perfect state of the system, if the model is right, everything plays well. And this has been well informed by the design here. So they are in a tight feedback loop. So we are able to produce behaviors for a system as complicated as this. But now the next step we are going to take is fuse all of these things together and see if we can actually take it to the hardware. Before going there, let's try to see what the real challenges are. Sensing is obviously one of them, because a lot of things are happening in a small space. It's very hard to sense the system because the quality of the sensors and most of the sensing techniques we have is optical. So there is a lot of occlusion, which makes things partially observed. For a second, let's just assume that we solve the sensing problem. There is still calibration and estimation problem. And most of these calibration techniques right now are either manual, where we position the thing and then measure where it is and do a regression on top, or it is optimization based. We both have their own complications. Manual calibration has gigs, doesn't have enough space to actually do a good job. Optimization based, because the dimensionality of the state gets stuck and gets misguided. There are two projects which I've done with different people. First one of them used optimization-based strategy to actually compute where the actual sensors are and corrects for that and does a little bit better job. In terms of manual calibration, we try to increase the length of the link by putting 3D printed object, do the calibration with that. It's a simple hack. If both of them improves the results. Yet, we cannot really assume that we are going to get a perfect reconstruction of the work because of just the dimensionality of the system is insane. So we have to deal with this complication saying that our estimation or modeling is never going to be perfect, and we have to deal with that. Let's see how we're going to do that. We're going to do that by a framework which is called learning from experience, and let's see what it is. The details of the trajectory optimization is when we give the dynamics model of the robot to the system, it does not use the dynamics of the system. Instead, what it uses is a linear approximation of the dynamics from the place you're standing right now. So while coming up with a global model of the system was very hard, now the linear approximation might be easier to get because it's a linear approximation in the local neighborhood. And that is the intuition we are going to play with. So we are going to use partial model of the system, and this partial model of the system is the linear time-varying model from the place you're standing. And we are going to adapt this model as we move along in the state space. So what it's going to look like is we have an agent which has some understanding of what it is doing right now. It's going to use its own understanding to execute the process a couple of times and collect a lot of samples. We're going to use this sample and fit a linear approximation of the dynamics, and we are going to go back to playing this game again of trajectory optimization. More formally, this is what the algorithm looks like, that we are going to initialize the policy using anything. And at each iteration, we are going to run that policy to collect a lot of trajectory samples, which are these samples. We're going to fit the dynamics model, which is the local dynamics, using GMM prime, and we are going to solve for trajectory optimization, which is minimization of an expected cost. And there is a KL divergence term which just says that the next distribution has to be close to the previous distribution because it's a linear approximation, and we don't want to make too rapid of a progress, or we might find ourselves in places where we have no idea how to act properly. So this is like, let's look at the results, how things look. Okay. So these are some of the learned behaviors. We are trying to manipulate an object, which is an elongated tube of coffee beans. Looks like this. and we are trying to turn it in along different axes. It is a very simple movement, and this is the training, how the algorithm learns. So we are at iteration 5, and we can see that already a lot of improvement is happening. It knows how to turn the cube. It has also started to investigate how to use the thumb as a pivot. And in addition, after being done with the thumb, it comes up with this very interesting behavior when it actually repositions the thumb and go for the extra push. And all of these details are coming straight from trajectory optimization, where the linear model is actually learned on the system. I'm going to skip the learning process on the simulation and go straight into what kind of behaviors have been learned in the system. So these are different behaviors. The objective is given down here. It just involves rotation along different axes or translation around different axes. As these are the building blocks of any movement, we want to understand them better to begin with. So there are simple behaviors where we go for rotation or translation across different axes. So as you can see, this linear approximation, if done right, is capable of coming up very, very complicated dexterous maneuvers. Not even just simulation, but in the hardware as well.
Do you have to choose a horizon for the future?
This is doing complete trajectory optimization at once. So we are solving roughly for 3.5 seconds in this case.
The constraint that you have with the KL divergence, is it
for
the whole future?
For the whole thing. Yeah, for the whole trajectory.
So it's open loop then?
No, there is a feedback component of the trajectory optimizer is giving us feedback along the whole trajectory. We just don't update the trajectory. So what we see on the left is a very interesting thing. It's not a scientific result, but it's an interesting observation that if we ask the human to do the same, which has not seen the task before, it comes up with the same strategy. But not initially, because there's a difference between these two, that in order to come up with a finger-centric approach, we lock the wrist. Otherwise, the hand just does this, which is an equally good strategy. Okay, so we lock the wrist. So we have to tell the human that, hey, try to spin it without using the wrist, and the human does exactly the same thing. Some numbers, this is how good we are doing on the y-axis. Lower is the better. The dotted lines are the simulation. The solid lines are in real hardware. And as you can see, for posing tasks, which is like just go to a random pose, you kind of make good progress. You get there pretty quickly. The cost that we use is just a distance metric to that particular pose, some regularization. For a twirling task where you're spinning the object along various axes, there are various runs. And the cost that we use is some regularization on the hand, what it means to be a good position, regularization on the control, plus the cost of the goal, distance from the goal for the object, where we want the object. And as we see, around about like 8 iterations or so, things have already saturated, and after that, it's just minor.
You should explain what's iteration.
Okay.
What's an iteration?
Yes. Each iteration of this algorithm looks like we collect a bunch of trajectory samples, fit the whole dynamics to the system, do a trajectory optimization, and come up with the next. So each iteration does the whole process.
And the whole bunch is
What's a bunch? Yeah. A bunch is.
A bunch is 5. Yes. So in total, this is doing something like 60 trials to come up with that.
The bunch needs to have some richness into it,
So-
like a persistence of excitation or something like
Yes. So what we do is instead of executing the same policy over and over, we inject a little bit of noise so that the system actually explores a little bit around the noise.
But each of those is then learned totally independently of all these other stuff things you learned.
Each of the
Like each of these behaviors or so.
yes, each of these behaviors
You're not
are
transferring
independent.
any information.
No, in this case, that would be ideal to do, but we are not. The next question is, are these policies robust? On the left, what we see is as we inject more noise in the initial state of the system, the trajectory starts to diverge, which is expected. And one way to solve this problem is to train with some amount of noise. But when we try to do that, things fail drastically because the initial policies are not rich enough to cater to these disturbances. But I already said around iteration 8 or so, we have already come up with reasonable strategies. So what we do is instead inject the noise after iteration 8. So you have made all the progress that you want to make, and now in order to reject the disturbances, now you inject robustness into your policy. That is what happens after iteration 8.
So prior iteration, is the noise just coming from just noise in the general system?
Yes, it's coming from noise, and if you're in simulation, then it's a perfect reset. There is no noise at all. You inject noise in the control policy to collect more samples, bigger samples.
Noise is not tricky because now you're going to fit a linear model.
Yeah. So
And then how can you guarantee that the model is not chasing the noise?
So that is exactly. So the black line embedded here is with perfect reset. We are only injecting noise in the initial state of the system. So if you're starting from here, instead of starting from here, start from a little bit. Okay. So there is one more. Yes.
By injecting noise in the initial state, are you telling it the wrong position, or are you just changing the initial position?
It gets an observation. Whatever your observation state is, if the observation state contains the rod angle, then it gets the rod angle. If it doesn't, it doesn't.
So the observation is noise-free?
The observation is noise-free in simulations, but in reality it has noise. So we are building a mapping straight from the raw sensor input to the raw voltage outputs of the valve. There's no estimation going on in between. It's raw.
Yeah, but you have really accurate sensors, so you might as well.
So you might
you
want to
might as
highlight
well
that
do
the
that.
object is actually in a motion capture lab. So
It is a motion capture lab. We are
In a
going,
sense, you're kind of sampling the neighborhood of your
Yes.
equilibrium,
Yes.
right? By
Yes.
initializing a
the
different.
different ones, yes. So one interesting details which I've hid till now is that we give the object to the hand. That is a very big assumption, right? And what it enables is that right from the first iteration, when you do a little bit of motor babbling, you understand if you're making progress or not. What if we take a task where the object is not in the hand? We are not going to get an initial results in which direction to make progress, and we are relying on a lot of exploration before that can happen. So in this particular section, we are going to have learning from imitation, and I'll go into the details. The task is we're going to pick up this tube from the ground. And no matter how much task details, variations, or cost tuning we do, this never happens. One of three behaviors emerge. Either the hand is doing random things on the top, no idea what the tube is doing in the bottom, or it actually finds the tube, and in order to explore the tube, it just knocks the tube out of the workspace because this is a free object. And the third thing is it keeps tapping on the thing with no idea what to do. The details of the task is that there is a big local minima that instead of reaching the tube from the top, which is exactly the closest point, you have to clear the tube, go to the bottom, and then only you can start to make progress. So it is a tricky situation to deal with. In order to deal with this situation, we are going to do learning from imitation. Previously, we were doing learning from experience. You experience everything and you learn by yourself. Here, we are going to do learning from imitation, and we are going to deploy an expert user to give imitation examples.
You need an expert to pick up the...
Yeah, it's very, very hard to find an expert.
Also, we pointed out the experts spent like 6 months collecting the imitation data and 2 weeks doing the rest of the research. So the data collection is the research, basically.
This is a virtual reality engine which allows us to get details of the manipulation. On the left is it being deployed in a variety of different conditions. On the right is what being deployed in this situation. What we see is the expert again giving a demonstration of picking up this object from the ground. So now we have one successful example for one successful case. Let's try to see how good this example is. Okay. In the next figure, let's just focus on one of them because each one of them is just different examples. So what we see is different rod angles on the x-axis, a notion of goodness on the y-axis, and this is black line is where the demonstration was given. Okay, and as we initialize the system away from the demonstration, what we see is the demonstration start to fail. So although imitation served as a good strategy at the position where you are, moving away might be challenging. And these strategies are brittle, as shown here, is right very close to the demonstration, there is a failure cases. All the greens are successful pickups, all the red crosses are where we actually failed to pick up the object. Okay, can we do something better than this? And the answer is yes. We are going to mix learning from imitation and learning from experience, and we are going to get a better solution to that. The way we are going to do is we are going to bootstrap the system using learning from imitation. We are going to say this, just take the expert's policy and start from there. And we are going to use the following cost function, which says stay close to the expert, There's some regularization of how much control you want to use, and there is an objective for you to achieve, which is pick up. So pick up the object at some height. And what we start to see is this interesting behavior. So I'm going to shuffle, and you will see the same figures, how the failure cases are kind of going away, and we are getting a better neighborhood where the demonstrations are quite successful, wider. Yes.
What's happening on the left again? Why are there still all these failure cases?
Oh, this one?
Yeah.
So this is pretty much like the end of the workspace for the hand. So it cannot go further on the other side. So it still somehow manages to do something good, which is pretty good. These are all random samples. This is, I could have evenly sampled, but these are random samples anyway. This is putting both of them together. The demos are blue, the GPS, which are the local policies, are green. Although the costs pretty much remain the same because it was an expert demonstration, so we were already doing pretty good. We will see the success rate or the robustness for a lot of these policies improved significantly. So the next immediate question that one will ask is, all of these policies are pretty local. You're solving such a big problem with so many demonstrations from one initial state. Can we actually go for a generalization where you can handle different variations of the task? Which is a pretty big problem on its own, that generalizing a policy that does hand manipulation is a big statement to make. In order to make the problem somewhat tractable, here is a reasonable problem we are going to study. We are going to study generalization in the various rotation angle of this tube, and we are going to again deploy the same technique which is learning from imitation and experience in this case as well. So here are the various demonstrations that we see, as each demonstration is the angle being rotated towards the right. And three clear strategies we observe in the demonstration. One strategy is that if the tube is away in this direction, then you have to curl the thumb inwards, go on the other side, and then reposition and go for left. If you're here, then this strategy kind of works. And if you're over there, the third strategy actually involves the rotation and then cut. So these are the three strategies that clearly we see in the demonstration. So we have to actually go for a generalization across three strategies. I would like to point out that these demonstrations were collected before any results or analysis was done. So these demonstrations are not cherry-picked at all. If they fail, they so be it. Let's just ask the question that each one of these demonstrations, are they good in the whole neighborhood? This is the entire neighborhood of the task, so all the angles. This is where the demonstration was given, and it doesn't succeed in the entire neighborhood. So this is a sanity check that each of these demonstrations does not work in the whole neighborhood. And these are all the demonstrations. But an interesting artifact is that if we try to do a cross-validation of one policy for that condition or that policy for the rest of the condition, we see there is a good diagonal over here. And this diagonal has a little bit of width, which basically says that this policy extends to the next closest neighborhood. So if we do something like a nearest neighbor, this should have a pretty good generalization, because the policies are kind of overlapping, which also tells us that these strategies are generalizable. That is in fact the case, that if we do nearest neighbor, we get about 90% of the success in the strategy. Here is some random examples. There is a random tube angle, and then you are picking up the tube from the random angle. This is by no way all the success one. There will be failures as well, and it will be pretty obvious how it fails. That is a failure case because it's not able to get the angle of the tube right. And there are cases where it actually knocks the tube out of its workspace and it has no idea how to do that, which is like this. So it has good success rate. However, there are few challenges in this case too. And the challenges here are that there has to be a notion of nearest neighbor. In this case, it was clear that there is a notion of nearest neighbor, which is in the tube angle space. But in the general manipulation setting, this nearest neighbor or the Euclidean metric or any distance metric might be very hard to compute. In addition, the nearest neighbor needs the object position. That is how we deploy the nearest neighbor, by looking at the angle of the tube. So can we do something better? And the answer to that is yes. Here is what we achieved. What we have solved right now is a nearest neighbor expert. So humans can only give us so much demonstration. We engaged an expert to collect some sample demonstration. We trained the local policies around those demonstrations and generalized using a nearest neighbor. What has just happened is by deploying this nearest neighbor policy, we have enabled ourselves to collect more trajectory samples where the humans are not the bottleneck. So more number of demonstrations can be collected, and we can do some learning on top of this. This is what the whole system is going to look like. On the top is the hardware. We are going to use the driver to get all the state that communicated back to the control layer. In the control layer, we use sockets to fuse the state. We are going to learn this global policy over here that is going to do a mapping from state to the controls. It's going to inject the control back into the system now. This loop is going to run as fast as possible. Okay, and this is what the whole results look like. Okay, this is neural networks. A lot of failure cases because it's a random sample in the first few iterations, but you will see it's a 75% success over a larger set. And even neural network is capable of upgrading. That's a failure case, by the way. So it is able to actually understand that if the tube is on the third strategy, you have to go for the rotation. If it's on this strategy, so it's able to come up with all these strategies. Interesting time. Short. And let's try to understand these networks a little better. So what we are going to see here is we are going to test this network on the observability of the network. So network is 6-layer, 150 unit with 75% success rate. Now here is a fully observable where we have the state of the hand and the object given to the network. We succeed 75% of the time. Here, instead of giving the state of the object, we give the touch sensor of the hand. So now external motion capture system dependence is gone, and we still see that based on just the proprioceptive sensor of the hand, the sensor which is contained in the hand is able to get similar success, which is pretty amazing. And we can drip apart the motion control system. It can still be used for training purposes, but during the final execution, we can take it away.
So on the left, when you have the state of the hand, the state of the object, that's the same thing that the nearest neighbor got.
This is the same. So now we are deploying nearest neighbor. So the way these things were trained is we generate a random cube angle, we deploy the nearest neighbor, and then we collect the sample.
No, what I'm saying is that, so this is the same condition, testing condition the nearest neighbor was trained.
Yes.
And it's 75%. Yes. So I thought when we were writing a paper yesterday, the story was at the time was the neural network was worse than nearest neighbor because it didn't see the object.
The neural network is 75%. The nearest neighbor is 90%.
Right, exactly. But the excuse we came up with is because we didn't see the object. But now you actually.
It's not. Wait. It's not there.
Okay.
Okay. So we are able to do well using the touch sensors. But we are using a very big network, a 6-layer, 150 units to a big network. And instead, we struggled a lot when we thought that 4 layers, 80 units is already a big network. We were not able to scale it up. And we went for a bigger network and actually solved the problem. And this is the comparison between what a smaller network does and what a bigger network does. This is where we actually make the whole network blind, that we are not even going to give you the state of the object as well as the touch sensor. Asking that is there an open loop strategy that works for everything? And
well, it's not open loop. It still sees.
It's a blind strategy. It's a blind strategy that works for
So it only sees the hand.
it only does about the hand. So it can understand the object by by sensing the state of the hand itself. If you're lifting a heavy object, your hand knows it's heavy. Just by the way.
In essence, you're asking the neural network what's the best strategy that works for all cases.
Yeah, like we asked the question. We don't know that.
Given those observations.
Yes. So we don't know everything. And the neural network is still doing comparable to what if it has the state. Here, the result is a little bit inconclusive, and I'll be upfront about it. I think what is going on is since all of these things were trained with the nearest neighbor, and the nearest neighbor, each one of these conditions has a different reset point, which is very minor bit different than the others, but still, there is some understanding if the reset was there, like this particular numbers, then the tube was here. So there is some information, I think, which is leaking in, and we have to do a careful investigation if this is truly blind or not, but that remains to be seen. Now, how do we do in the robot? Here, instead of going for a generalization just in the angle of the tube, we are going for a generalization in both the angle as well as the position. So the angle diversity is not that huge as previous, but still both. Here is the training set that we have given. There are 2 angle deviations and there are 2 position offset given to the system. On the right, the video soon. On the right, we do clause validation where the policy 0 was for initial condition A, so the diagonal is all success. And as we go away from that particular neighborhood, we see that the performance is decreasing. Each one of these policies are not succeeding that great on any random initial position of the tube, whereas the neural network overall does a pretty good job across different initial conditions as well as on the random initial scale of the object. There is anyway, this is the pickup strategy which neural network policy is doing on the Android system, and this has been somewhat cherry picked to show you what all the successful and all the failure cases look like. So we will see like how if it fails, how it fails. So these are the successful cases where it actually understood, and their platform down here is like if we can position the rod on the platform, then we want to generalize. That's the idea. So that's another success case. There are a lot of failure cases in yeah. Yes, that's a failure case because it picked one end of the rod where the other end kind of fell down. So the pinky of the finger didn't engage properly to get it right.
Does look like a problem you could maybe handle pretty easily or not.
It's probably kind
of ways to equate line and then whatever.
You would think it is possible, and I agree with you, but actually it turns out not. Coordinating 5 different people together is a hard job, and that's what it is. 5 of the fingers have to agree on each other. That the thumb has to provide the pivot before these fingers start to push, otherwise we want to just knock everything down. If you want to rotate, the thumb has to be flexible to be patient and stuff. So I'm assuming it showed both the failure and the success cases, and I tried to cover everything that looked like a failure and looked like a success. The rest looks kind of same.
Is this initialized with demonstration?
Yes, the demonstrations were given over. Like these 4 lines are the 4 demonstrations.
But how are they given with the like remote control of the hand or?
Yeah, like the same thing. Like with Joko haptics, you use the cyber glove to control either the simulation or use the cyber glove to control.
So you control the cyber glove
that mimics the hardware. Yes, okay. You do tele-op on the hardware using cyber glove and collect demonstration. Train a policy around that demonstration. Use that policy to collect a lot of samples, 20 per policy in this case. So we have 80 samples to train the neural network. And that's it. Okay, let me try to wrap things up now. So this thesis makes contribution across 4 different fields. First, we looked at a manipulator, which is flexible, capable of hosting dexterous manipulation, and we have seen some example of it actually doing performance. When we try to aim big, there is always challenges. In order to wrap those challenges properly, we've developed hardware abstraction that tries to hide all the challenges and expose the good part of the flexibility of the manipulator. I also would like to point out that this result is somewhat more of a general because these abstractions or pneumatic abstractions can be used in a variety of different robots. It doesn't have any dependence that it has to be used on the hand. And that is what the field has also been looking for and waiting for because the robots are actually going to come up in the wild and they want to be safe, they want to be lightweight, they want to be compliant. So this is going to go a long way in that direction. We have also come up with a behavior synthesis framework which generalizes well, at least it has capability of planning. We introduced the concept of dimensionality augmentation that instead of killing the dexterity, it preserves the dexterity as well as gives us a good tool to navigate complicated landscapes. And finally, we pitched everything together into the hardware and came up with a solution which is sample efficient. And it works with free floating objects, and with a very high dimensional system. So all of these things put together makes this result really unique, which has not been demonstrated before a lot of the times. In terms of the future direction, I still want to probe the intersection of doing stuff in simulation, getting some demonstration, and being sample efficient while transferring these results on the real hardware. And I also want to investigate a little bit into learning with physics prior, because each of these things are happening right now independent, and it would be good if we can incorporate some learning from the physics into learning in the wild. In the long term, I want to work towards breaking this paradigm that there is one task for one manipulator. We want to have manipulator which is successful more generally and for more complicated things, and they should be safe and should be deployable in the real world. While last decade was about locomotion, I think the coming decade is going to focus a lot more on manipulation, because now we have capable robots that can come, they are intelligent, they can smart. All the AI agents have become smart enough that embodiment is now a problem. We have seen a lot of commercial companies deploying toy robots that can talk to you or give you direction. So embodiment is actually in the forefront now, and it's about to happen. And when this is about to happen, the principal requirement of embodiment is going to be interaction. That is what an agent does. It interacts by touching, making contacts, making communications, etc. And it's going to be somewhat interesting to see. The hardest slide to make is this one. Everyone helped me get here. If one of the steps didn't work, probably nothing could have been done. So I really want to thank my advisors, Amol and Sergey, and the committee over here, and my family, mom, dad, and my two brothers, Shashank and Sean, and amazing suite of collaborators that I've worked over time, CSC, different institutions I've been a part of, some special ones, some friends. Thank you. All right, I've everything clear or a lot of questions? Questions? Yes.
On the dimension augmentation, you mentioned one of them, which is you had this one kind of feature where you're grouping multiple fingers that kind of move together.
Yeah.
Are those hard coded? Are you grouping actions there, or how do you select those?
Yeah, it was hard coded. We just wanted one dimension with hand, just completely open and completely closed. It was not cherry picked. We just said like, okay, all the dimension that closes, because it's an antagonistic system. So there is one actuator that closes things, and one actuator that opens things. Just said all the actuators that close things, if it is negative, then you should close. If it is positive, then you should open. The other one should open. So it's just like a very naive close and open strategy. But it aligns very closely with the principles that PCA dimension of the hand dimensions.
Have you explored that more in other like groups of actions?
I tried other PCA dimension, which is like opening and then like this. And first was good enough to get very good results. So you can get a little bit more performance if you add a couple of more, but in this case, at least the first one was good enough to make the problem not work to work. Yes?
So in the past, what types of controllers are typically used with pneumatics?
With the pneumatics, simple PID controllers. People have done a little bit of modeling and tried to come up with some feedback term, but it is not. It is really like if you want to make a step change, if you look at the papers, they take like 5 seconds to do that. And we are doing in the resolution of milliseconds. So it's like an order of time step reduction, like time step reduction. So the result that I showed.
So this is maybe a more conceptual question, but
Yes, go ahead.
No.
Thank you.
Hello. All right, we'll see when we come back. But yes, if we look at the papers, they take an order of seconds to achieve a step change that we're doing in seconds. And the results that I compared with, which was TIDF, is what Emil did, which is again like it takes the model of the system, both the pneumatics as well as the model of the entire.
Sorry, I think there's just a lot of lag on the remote connection, but.
Yes, Sergey, go. I'm listening to you.
Well, like you said, there's
Talking to ourselves.
let's use something else. Send him a message to use Hangouts. I'll I'll try to find.
Okay. Yeah. Let's try to call or something. If someone has Sergey's number.
Yes.
Everybody has Sergey's number. Anyways, I can take next question. Yes.
Actually, what are some of the factors that cause the leakage in the data that you are providing?
For training the network?
Yeah, for training the network.
So the leakage information is coming from the way that we are giving the samples for training. If it was a truly random sample that covered the whole space, then it will have to generalize across it. But these samples are generated using nearest neighbor, and there are like these bunches of samples that are distinct from each other when they start. So based on just the initial point, we can say this sample actually started from this condition. So there is some leakage of information coming from there. And for a truly random sample set, that each of these neighbors should have like random initials.
So isn't that, hold on, isn't that there's just the random initialization of the object on the hand? Does the hand not?
The hand also, like, so there is no perfect reset for the hand. Right? Every reset, right, because it's the nearest neighbor, it has one reset condition. It's not exactly precisely 0, 0, 0, 0. It's some random numbers close to 0.
How hard would it be to generalize it to a case like really where the hand, I mean, you have this hand attached to this cool arm.
Yes.
Which you're already using.
Yeah.
So just like you put the object there and the hand just has to come in and grab it.
I think it should be doable fairly easily. However, I have to say that my interests are like really get the finger details because that is what is missing. And that is why I'm trying to constantly constrain the system so that the finger details emerge. I've even logged the wrist so that you can come up with finger behaviors. So doing the hand will be easier than looking at the right now. But it's still going to be a good amount of work. It's not going to be like the easiest part, but it's probably going to be easier than looking at the right.
All right, so if we don't have more audience questions, let's
Yes.
switch to the. Sergey, wait for.
Sergey, Mo is asking to wait for the closed session. We are going to kick people out.
Unless you want to make a public announcement.
People feel free to be kicked out.
Okay.
Feel kicked out.
So this will be the end of the public session. You should wish me luck before going. I know that happens.